Hey, this is Wastewater Treatment Certification Training, Chapter 6, Digesters. Digesters are used to process the wasted activated sludge in order to concentrate the solids. You do this to reduce the volume of the wasted sludge to help reduce your disposal cost. Sludge on its own has poor mechanical dewatering characteristics, so it needs to be treated, and typically still you end up using a polymer to dewater it. Higher energy costs and capital costs may be incurred if you use digesters. There are two types of digesters: aerobic digesters, which is just like it says, it requires oxygen for the bacteria to digest the sludge, and anaerobic, that uses anaerobic bacteria, acid formers and methane formers, to help concentrate the sludge and produces methane as a byproduct. Aerobic digestion can occur in either an open or a closed tank. The microorganisms are grown in the endogenous respiration phase. What that means is food is scarce, so the bacteria consume their own cell contents or the remains of dead microorganisms to obtain energy. Because the food is so scarce, no new bacteria are formed in this phase, and you add no new organic material to the tank since you're just adding sludge. The advantages of aerobic digestion: you produce a lower BOD concentration in the supernatant liquor than you do with anaerobic. Aerobic digestion produces an odorless biologically stable end product that's humus-like. They're very easy to operate. They cost less to build, so you have lower capital costs. You can do continuous or batch treatment followed by settling and decanning. And in cold weather, the digester can be used to store sludge as a holding tank. Disadvantages of aerobic digesters: you have high operating power costs due to the constant aeration. And aerobic digesters do not improve the dewatering characteristics of the digested sludge. Concentration of solids: 75 to 80% of the cell tissue is broken down into carbon dioxide, water, and ammonia. Ammonia is then converted to nitrate. Pre-treatment, your sludge is 1 to 2% solids. Post-treatment, your sludge is about 5 to 8% solids. 25% that is not broken down is inert or organic compounds that are not biodegradable. Alkalinity is needed in aerobic digestion. Since you do convert ammonia to nitrate, you need 7.2 pounds of alkalinity per pound of ammonia that you're converting to nitrogen during the nitrification. A pH drop can occur if the alkalinity of the wastewater or the sludge is insufficient to buffer the solution. You may regain some of this alkalinity during the denitrification step. Factors to consider for aerobic digestion is everything we always teach. We say temperature is a factor. Digestion will go faster as the sludge temperature is warmer. Your dissolved oxygen requirements: you still need oxygen going to your tank for the sludge to digest properly. Tank volume: your tank must be big enough to hold the sludge that you're trying to treat. Sludge characteristics: you have to know what % solids reduction you can hit with your particular sludge. Loading rate: how much sludge you can add to your tank. and the energy requirements for mixing. You must have a mixer capable of stirring the sludge. Some aerobic digestion math. You need to run a specific oxygen uptake rate, or SOUR. It's a measure of the oxygen used by microorganisms in the digesters and determines the biological activity and the resulting solids reduction. A common range is 5 to 10 milligrams per gram volatile suspended solids per hour during active digestion. Well-digested sludge is 0.5 to 5 milligrams per gram volatile suspended solids per hour. You have to calculate your oxygen uptake rate before the SOUR can be calculated. The formula is there. The oxygen uptake rate in milligrams of oxygen per liter per hour is the DO at the start of the test, or DO1, minus DO2, which is the final concentration of DO, divided by your time 2, time at the end of the test, minus time 1, time at the start of the test. You do all of that first, then you multiply it by 60 to convert it from minutes to hours. The formula to calculate your SOUR is SOUR equal oxygen uptake rate times 1,000 divided by your volatile suspended solids in milligrams per liter. So if you can write it out longer, it'll be the SOUR equals the milligrams per liter of DO drop per minute times 60 times, because that's the oxygen uptake rate, times 1,000 divided by volatile suspended solids in milligrams per liter. The units of SOUR are milligrams of oxygen per gram of volatile suspended solids per hour, which is why we multiply 60 and 1,000 to we put the units correct. Then we got the hours from the 60 and the milligrams from multiplying it by 1,000. So SOUR math, the MLVSS, which is the volatile suspended solids, is 2,200 milligrams per liter. The initial DO was 7.2 milligrams per liter, and 10 minutes later, the DO is 4.2 milligrams per liter. What is the SOUR, or specific oxygen uptake rate, in milligrams of O2 used per gram per MLVSS per hour? There's the formula again, is specific oxygen uptake rate equals oxygen uptake rate times 1,000 divided by volatile suspended solids, which is your MLVSS in milligrams per liter. So we'll work through this one together. First, determine the oxygen uptake rate. Your initial DO was 7.2. Your final DO was 4.2. So you subtract that and you get 3 milligrams per liter. Time 1 was 0, time 2 was 10. So you had the 3 milligram per liter DO drop in 10 minutes. Take your 3 milligrams per liter divided by the 10. You get 0.3 milligrams per liter DO drop per minute. Then you multiply that by 60 to convert to hours. And your oxygen uptake rate for this case was 18 milligrams per liter per hour. Now that's just the first part of the calculation. Once we know our oxygen uptake rate, we can plug that into the equation along with our MLVSS. So our specific oxygen uptake rate is going to equal 18, which was our oxygen uptake rate, times 1,000 divided by 2,200 milligrams per liter, which was our MLVSS concentration. Do the math. your specific oxygen uptake rate is 8.18 milligrams of oxygen per gram per hour. Now you know what's going to happen when I push this button. Here's one for you to work out. You go ahead and try to work it out, and I'll give you a few minutes, and then I'll come back and we'll work it together. Okay, the MLVSS is 2950 milligrams per liter. The initial DO was 6.9 milligrams per liter, and 15 minutes later, the DO was 3.2 milligrams per liter. What is the specific oxygen uptake rate in milligrams of oxygen used per gram of MLVSS per hour? Which number did you get? The correct answer is C, 9.15 milligrams of O2 per gram of MLVSS per hour. Let's see how we got it. Your initial DO was 6.9. 15 minutes later, the DO was 3.2. So 6.9 minus 3.2 would give you 3.7. Divided by 15 minutes means your O2 dropped 0.45 milligrams per liter per minute. Multiply that by 60, that gives you 27 milligrams of oxygen per liter per hour. That is your oxygen uptake rate. So you put that into the specific oxygen uptake rate equation, 27 times 1,000 times your MLVS, or divided by your MLVSS, that is 2950 milligrams per liter. Do the math, and your specific oxygen uptake rate equals 9.15 milligrams of oxygen per gram per hour. Remember, on the math, there are more examples in your wastewater manual. There's also a math study guide on our website under test preparation materials for the wastewater math. This is your design criteria for aerobic digesters. This is in your book. It's there as a reference document for you to use while you're working. Now we'll go to anaerobic digesters. Anaerobic digestion involves several groups of anaerobic and facultative bacteria breaking down and assimilating, or putting together, organic matter in the absence of oxygen. Anaerobic digestion produces methane, which can be captured and used for heat or to produce electricity by burning it in a generator. The stages of anaerobic digestion. Stage 1, the complex organic materials are broken down into simpler compounds that the bacteria can use. Stage 2, the acid-forming bacteria, the saprophytes, convert organic compounds into volatile organic acids, fatty acids, or volatile acids. Stage 3, the methane fermenters convert these acids into methane and carbon dioxide. So it's a 3-step process. Anaerobic digestion, the rate of acid formation and methane formation should be approximately equal. Methane fermenters function best at a pH range of 6.6 to 7.6. The typical pH range for digestion is from 6.8 to 7.2, just like it is in your wastewater plant. The reactions that take place in the acid formation, raw sludge is broken down by the acid formers to produce CO2 in organic acids. The methane formation is the organic acids are broken down by the methane formers to make methane and CO2 and some water and hydrogen sulfide. Bioreactor gas is typically 65 to 70% methane, 25 to 35% carbon dioxide. There's also some hydrogen sulfide in there. Factors that affect performance are temperature, pH and alkalinity, volatile acid content, solids loading, and the detention time and mixing in the digesters. The different types of anaerobic reactors are standard rate and high rate. A standard rate digester, the contents are usually heated, but can be run at ambient temperatures and are unmixed. Typical detention times for digestion is 30 to 60 days. The high rate digestion process contents are heated and completely mixed. Detention times are typically 10 to 20 days for this digestion to be complete. A combination of these two basic processes is known as the two-stage process. In a single-stage standard rate reactor, you'll see everything is stratified in the reactor. Everything has layers. The raw sludge comes into the active digestion part of the reactor. That can be recirculated to a sludge heater if you're running a hot digester. You're not running at ambient temperature. As your digestion takes place, the digested sludge will settle to the bottom where it can be removed from your digester. The supernatant, or the clear liquid, will be on top of the active digestion layer, and that has to be removed and treated. It has a lot higher BOD than an aerobic digestion supernatant. You also develop a layer of scum that must be removed and disposed of, and then the natural gas and CO2 are stored in the gas storage part of the tank where it can be removed. On the two-stage high rate, the first stage is a completely mixed reactor. You see there's a sludge heater. Your raw sludge goes in. There's a mixer that keeps it mixed in the digester. So you will have gas storage at the top of that reactor. And the sludge is then moved over into the second stage, which is stratified. Your digested sludge stays on the bottom. The supernatant liquor comes out above it and can be removed. There's a layer of scum that has to be removed, and then your gas storage. And both of these will produce gas. Typically, the second stage will have a floating cover. The temperature ranges for the digesters. If you're running ambient, you're probably using either sacrophiles or mesophiles for bacteria. The sacrophile range, the optimum temperature is 50 degrees Fahrenheit. Mesophiles range from 68 to 113. So if you're heating the reactor some, you will be using mesophiles. But typically when you're heating, you'll use thermophiles. The range for these are 105 to 150 degrees Fahrenheit. Their optimum point is probably right about 140. For digester startup, like we said, covers can be fixed or floating. If you've got a floating lid, a floating cover, you need to make sure as you're drawing air or you're drawing sludge out of the top that you don't let air get in your reactor with either cover design, either fixed or floating. If air mixes in the proper concentrations with the natural gas, it can trigger an explosion, as you can see in this picture that's attached to this. As you're starting up, check all water, gas, and sludge lines for leaks. Then you add water or raw wastewater, not sludge at first. You seal the cover, mix, and bring to temperature before you begin adding raw sludge. You do this to reduce explosive gas mixtures. Remember, the main product of anaerobic digestion is methane, and it is explosive. The lower explosion limit for methane is 5% in air. The upper explosive limit is 15% in air. So if you get between 5 and 15% in air, methane will explode. Septic conditions can occur if you add too much raw sludge. If you add too much, the acid fermenters will predominate, lowering the pH and creating undesirable conditions for the methane fermenters. Sludge feeding should be often and in low concentrations. Low pH will cause the digester to go septic or sour, and it will take you about 30 to 60 days to recover from this condition. Recovery from a sour condition can cause foam or froth due to CO2 and methane production. Forced sludge solids through water seals and gas lines, and you'll have serious operational issues you have to try to overcome to bring this reactor back from a septic condition. The loading of the digester with volatile solids can be calculated to reduce the incidence of overloading. You can calculate the solids loading rate, the organic loading rate, and the volatile solids loading rate. Digester loading rate math: pounds of volatile suspended solids per cubic foot of digester space per day is the solids loading rate. So it's your volatile solids applied or added in pounds per day divided by the digester volume in cubic feet. The sludge loading rate is dependent upon temperature and the volatile acid to alkalinity ratio. To calculate the digester loading rate, let's work through one of these together. Calculate the volatile solids loading rate in pounds of volatile suspended solids per cubic foot on an anaerobic digester if the waste sludge flow is 9,500 gallons per day. The TSS is 3.8%. The VSS is 65% of the TSS, and the digester volume is 60,000 gallons. So we'll use the pounds formula for the top part of the equation. There will be conversions you have to make, and you convert the gallons into cubic feet for the volume. So let's look at the math. Convert gallons to million gallons. Your flow is 9,500 gallons per day. Divide that by a million. That means your flow in million gallons is 0.0095 million gallons per day. Calculate the volume, the concentration of your volatile suspended solids. The problem said your solids, your TSS, were 3.8%. If you look on your formula sheet, you will see it says 10,000 or 1% equals 10,000 parts per million. It's typically down with the pounds formula down in that area. So since 1% equals 10,000 parts per million, take your 3.8 times 10,000, and 3.8% TSS becomes 38,000 milligrams per liter of TSS. Now, we also said in the problem that the VSS, volatile suspended solids, were 65% of the TSS. When you use a percent in a calculation, you have to take that 65% divided by 100 and gives you 0.65, and that's what you use in your equation. So 38,000 milligrams per liter of TSS times 0.65, that's the part that's volatile suspended solids, gives you 24,700 milligrams per liter of VSS. Now we can use the pounds formula. Pounds equal your flow, 0.0095 million gallons per day, times 8.34, which never changes, times 24,700 milligrams per liter of volatile suspended solids, which will give you 1,956.98 pounds of volatile suspended solids. We need to convert our gallons of our reactor into cubic feet. We have 60,000 gallons. We know there are 7.48 gallons per cubic foot. So 60,000 divided by 7.48 gives us 8,021.39 cubic feet. That's our digester volume. Now we can solve the equation. The volatile solids applied in pounds per day divided by the digester volume. We had 1,956.98 pounds of volatile suspended solids divided by the digester volume of 8,021.39 cubic feet. And that gives us a digester loading rate of 0.24 pounds of volatile suspended solids per cubic foot. Here's one for you to work out. Calculate the volatile solids loading rate in pounds of volatile suspended solids per cubic foot on an anaerobic digester if the waste sludge flow is 12,000 gallons per day, the TSS is 5%, and the volatile suspended solids is 63% of the TSS, and the digester volume is 75,000 gallons. This is in the format you will see on test day, where there's the problem and then 4 answers to choose from. Okay. What did you get for the answer? Correct answer, 0.31 pounds of volatile suspended solids per cubic foot. Let's see how we did it. First, we have to convert our gallons to million gallons. 12,000 gallons divided by a million gives you 0.012 million gallons per day. We have to calculate the concentration of volatile suspended solids. 5% TSS equates to 50,000 milligrams per liter of TSS. 5.0 times 10,000 milligrams per liter per percent. To get the volatile suspended solids, the problem said it was 63% volatile. So you take your 50,000 milligrams per liter of total suspended solids times 0.63, 63 divided by 100. And that gives you 31,500 milligrams per liter of volatile suspended solids. Use the pounds formula. Pounds equals the flow, 0.12 million gallons a day, times 8.34, times your volatile suspended solids concentration, 31,500 milligrams per liter, which gives you 3,152 pounds of volatile suspended solids. We have to convert the size of our digester from gallons to cubic feet. So 75,000 divided by 7.48, there's 7.48 gallons per cubic foot. 75,000 divided by 7.48 gives you 10,026.7 cubic feet. Now you can plug the volatile solids applied, pounds per day, and the digester volume in cubic feet into the solids loading rate problem. 3,152 pounds divided by 10,026.7 cubic feet gives you 0.31 pounds of volatile suspended solids per cubic foot. The volatile acid to alkalinity ratio. The production of volatile acids by the acid fermenters and their ratio to alkalinity is key to digester performance. Low volatile acids in high alkalinity will drive anaerobic digestion. For example, 120 milligrams per liter of volatile acids and 2,400 milligrams of alkalinity. This ratio should be checked at least twice a week, if not more often, and maintain it on a trend chart so you can see if this ratio is going up or going down. During satisfactory anaerobic digestion, alkalinity will range from 1,000 to 5,000 milligrams per liter. Volatile acids will range between 50 to 300 milligrams per liter. The volatile acid to alkalinity ratio must be maintained at less than 0.25. So your acids divided by alkalinity, you want that number to be less than 0.25. If you're in the 0.3 to 0.4 range, that means the digester is stressed. It's having a hard time doing what it's supposed to do. If this ratio is 0.8 or higher, it indicates failure. You've got a septic condition in your reactor, 30 to 60 days to turn it around. Digester failure may have already occurred before a drop in pH levels can be detected. That's why you use this volatile acid to alkalinity ratio. You run it at least twice a week. You plot it on a trend chart similar to the one you see. You'll draw your points and plot it. You want to stay below 0.25. Remember, from 0.3 to 0.4, the reactor is stressed. 0.8 and higher, your digester has failed. Okay, we're done with the anaerobic digester. Now you've either digested your sludge aerobically or anaerobically. Now you've got to get rid of your sludge. What you have to do first is you want to remove more of the water contained in the sludge before final disposal, thus reducing the sludge volume and reducing the cost to dispose of this sludge in a landfill. You can either use pressure filtration with plate and frame filters or belt filters. You can centrifuge the sludge to remove the water, or you can use sand drying beds. The plate and frame press, this is batch operation. It's vertical plates held in rigid frames and pressed together. The sludge passes through the fibers of cloth mounted on the face of each plate, and the cake will build up on those plates. The removal efficiency is affected by sludge type, conditioning you may have done with polymers, filter pressure, filtration time, solids loading, and the type of filter cloth you used. When your press is full, you release the pressure on the plates and scrape the solids into the wagon you see there below that press. You can use a belt press. For belt presses, the sludge is preconditioned with polymers and then applied to the free water drainage zone of the filter belt. Water is forced from between the belts, and the retained solids are scraped from the two belts when they separate at the discharge end of the press. So you see your polymer or your sludge is being added to the gravity section of the belt. As the belts rotate around, the sludge is pressed between the belts to remove the water. At the top, the belts come spread apart again, and the pressed sludge is scraped off the belt into the receiving container. You can use centrifuges. Solids are separated from the liquid phase by centrifugal forces and are compacted against the wall of the centrifuge. There's two basic designs. There's a batch operated basket centrifuge. You put your sludge in, you spin it in the centrifuge to get all the moisture out. Then you open it, clean out the solids, fill it again, and go that way. Or you can use a continuous flow scroll centrifuge where the solids come in, they're compacted, the water goes out, the solids are scraped off the scroll, and the solids come out into your storage. You can use sludge drying beds. Usually with sludge drying beds, if you spread the sludge 8 to 12 inches deep, it will result in dewatered sludge that could be ready for removal in 3 to 4 weeks during warm weather. Weather really impacts your drying beds. Fresh sludge should never be applied to a bed already containing partially dried sludge. Addition of polymer to your sludge before you spread it may speed up drying time. Factors affecting drying time: sludge conditioning, if you use polymers or not, the weather conditions, You can imagine in the winter and in the wet season, it's going to take a lot longer to dry sludge. I've seen some drying beds in parts of the state that they now cover their drying beds to help them use them year round. It also depends on your application rates and depths in the beds, and actually how you remove the dewater sludge from the sand. You can see if you clean it properly, you go right down to your sand bed, then you can lay the sludge right on top of that. Sludge disposal. Sludge should be dewatered to between 45 to 60% volatile solids to improve drying efficiency. Before the sludge will be allowed to come to the landfill, it must pass the paint filter test. That's where you take sludge, you put it in a filter. The sludge has to sit for a certain amount of time with no water coming through the filter. You have to run a T-clip, the toxicity characteristics leaching procedure, to look for metals and other chemicals in the sludge. And your sludge must be adequately digested, which is a nice way of saying it can't stink. And that's the end of digesters. If you have questions, you can send an email to envhelp@ky.gov or call 502-782-6189 and leave your question. They will be forwarded to a trainer, and the trainer will get back with you to help you with the problem.